All right, let's talk about a tool that every good consultant should have in their back pocket, the Friedman test. You know, for those times when your data is, well, messy. Real-world messy. The kind of data that doesn't play by the rules of a perfect statistical model. So let's break down exactly what it is and how you can use it.
So, let's put you in the hot seat for a second. Imagine you're in that big stakeholder meeting. You've just finished testing 3 new software UIs on the same group of users. You have the feedback, but when you look at the data, it's not a nice, clean bell curve. It's all skewed to one side. So what do? How do you stand up there and confidently say, this is the one that works best? That's the exact problem the Friedman test is built to solve.
Okay, here's how we're going to tackle this. First, we'll dig into the exact problem this test solves. Then, we'll get into the nitty-gritty of what the Friedman test is. After that, we're going to roll up our sleeves and walk through an actual example. And most importantly, we'll talk about how to take a statistical result and turn it into a real-world decision. Finally, we'll touch on the limitations, because every tool has them. It's a straight shot from the why all the way to the so what. So first things first, let's talk about the why. Before we even get into the mechanics of the test, we really need to get our heads around the specific problem it was designed for. What's that business pain point where the Friedman test suddenly becomes a total lifesaver?
So the core situation is actually super common. It's when you're measuring the same people or the same things over and over again, but under different conditions. Think about it. It could be a patient's health over several months of treatment. Or, like in our software example, it's that same group of users reacting to different designs. The key here is you've got these repeated measurements, but the data is messy. It's not that perfect bell curve you hope for.
Okay, so this is really the key decision point. It's all about knowing which tool to grab from your analyst toolkit. Look, if your data is just perfect, a beautiful normal distribution, then sure, a repeated measures ANOVA is your best friend. But what about when it's not? What happens when your data is based on ranks, or it's just skewed? Well, that's your cue. That's when you pivot. That's the moment you say, okay, time for the Friedman test. It's the non-parametric alternative that's actually built for how data looks in the real world.
All right, so we've got the why locked down. Now let's move on to the what. What exactly is this test? Let's unpack its core principles.
So when you strip it all down, the Friedman test is a non-parametric way to see if there are real differences across 3 or more related groups. Now there are 2 magic words in there. The first is non-parametric. That's just a fancy way of saying it doesn't care if your data is a perfect bell curve. And the second is related groups, which just means you're testing the same people or things multiple times. And just so you know, this isn't some new unproven trick. No way. This test has been around since the 1930s. It was developed by the economist Milton Friedman. Yeah, the Nobel Prize winner. So this idea of using ranks to analyze data, it has some serious history and credibility behind it. It's been a trusted part of the statistician's playbook for a very long time. Now, of course, like any statistical test, there are a few ground rules. You need a random sample, you have to be measuring your group at least 3 different times, the usual stuff. But honestly, the last assumption on this list is the real game changer. It's the one that says your data doesn't have to be normally distributed. And that, right there, is its superpower. It just lets you bypass one of the biggest headaches in data analysis.
Okay, so that's the theory. But theory's one thing, right? Let's get our hands dirty. How do you actually run this thing? In this next part, we are going to walk through a real-world example, step by step, so you can see exactly how the sausage gets made.
So let's dive into a case study. Imagine a public health department rolls out this brand new water cleanup system. The big question is, of course, is it actually working? To find out, they measure the level of a certain contaminant, it's called THM, across 12 different counties. And they do it at 3 points in time: before the system was installed, 1 week after, and then 2 weeks after. The whole process really boils down to 4 straightforward steps. First, we take all our raw numbers and we rank them, 1 county at a time. Super simple. Second, we add up the ranks for each time period, so a total for before, week 1, and week 2. Third, we plug those totals into the Friedman formula and it spits out a single number called the Q statistic. And finally, we take that Q value and use it to make our decision. That's it. That's the whole process.
So this is what the raw data would look like in a spreadsheet. Each row represents one of our blocks, which in this case is just one of the 12 counties. And each column is a treatment or a condition we're testing, which for us is just the point in time we took the measurement. So you can see we've got 12 blocks and 3 treatments.
Okay, step 1, ranking. This is where the magic starts. You literally just go row by row, county by county. So for county 1, you find the lowest contaminant level and give it a rank of 1. The next lowest gets a 2, and the highest gets a 3. Then you just do that again for all 12 counties. Once that's done, for step 2, you just add up all the ranks in each column. That gives you your grand totals at the bottom.
So we take those rank totals, we plug them into the Friedman formula, which you can find in any stats program, and boom, we get our number. Our test statistic, our Q value is 20.16. Now this single number is the key to everything. But, what on earth does 20.16 actually tell us?
And that brings us to, honestly, the only part that really matters in business. This so what? We have a number, 20.16. Great. Now we have to translate that number into an actual, meaningful, data-backed decision. Okay, so with any test like this, you've always got two stories competing against each other. The first is the null hypothesis. Think of this as the default, skeptical view. It says, nope, the cleanup system did absolutely nothing. Any changes you see are just random noise. The other story is the alternative hypothesis. That's our theory. It says, hold on, the system did have a real, measurable effect on those contaminant levels.
And making the call is actually pretty simple. All we do is take our calculated Q value, our 20.16, and we compare it to a critical value you'd look up in a stats table. It's like a high score contest. And in our case, our score of 20.16 is way higher than the cutoff. So what does that mean? It means we get to reject that skeptical null hypothesis. The evidence is clear. We can say with confidence that the cleanup system had a statistically significant effect.
So that's great news, right? We have a result. But hold on. A great consultant never stops at the first answer. We always ask, what's next? See, the Friedman test just gave us a big thumbs up. It told us that there's a difference somewhere in our data. But it didn't tell us where. Is the big drop between before and week 1, or maybe between week 1 and week 2? Where exactly did the change happen? And this is a really, really important point to remember. The Friedman test is what's called an omnibus test. Basically, it just tells you, yes, a difference exists somewhere in this group. That's it. To actually pinpoint where that difference lies, to compare before versus week 1, for example, you have to run a follow-up analysis. These are called post-hoc tests. You can think of the Friedman test as the alarm bell, and post-hoc tests, like the Nemini test, are the tools you use to find the exact source of the smoke.
Okay, last but not least, no tool in your toolkit is a magic bullet, and a smart analyst always knows the pros and the cons. To really use the Friedman test like a pro, you have to understand its limitations. It's all about having a balanced, clear-eyed view of what it can and can't do.
And really, here's the big trade-off you need to know about. All that flexibility you get from not needing normal data, it comes at a price. And that price is statistical power. In simple terms, the Friedman test is a little less sensitive than something like an ANOVA. That means if there's a very small, very subtle difference in your data, the Friedman test might miss it. That's why you don't just default to it. If your data actually is normally distributed, ANOVA is still the more powerful, more precise instrument. And there you have it. That's the Friedman test, from top to bottom. We've covered the exact problem it solves, how it works, and how to turn its results into a solid decision. You now have a really powerful and practical tool for dealing with the kind of messy, real-world data we all face. So the only question I have for you is, what hidden trends are sitting in your data right now, just waiting for you to find them?